Hello dear students, welcome back to chemistry classes. Today we are discussing conversion of two-dimensional square close packing into three-dimensional. Okay, here this up to this spheres, it is a two-dimensional square close packing. This is the first layer. The same layer is placed exactly back to the first layer. It looks like this. This is the second layer. This is what? This is first layer. This is second layer, isn't it? Okay. When we draw the lines of the spheres, center of the spheres, here one sphere is there, back side sphere. It looks like this. Cubic, isn't it? It is cubic close packing, isn't it? This looks like cubic close packing. Here arrangement is AAA type arrangement. This is the first layer and this is the second layer. When we draw these centers, we are getting one cubic structure, isn't it? This is our first concept. Okay. Here conversion of two-dimensional hexagonal close packing into three-dimensional close packing. Okay, what happens here? Here in the first layer, in the second layer are occupy the position that depressions created by the first layer, isn't it? Okay, like this we are form a one layer. The same layer, like this layer, we have to apply on the first. This is the first layer. We have to add a second layer on the first layer, like the depressions created by the first layers. This layer having a depression 1, 2, 3 like this. These are the depression. What we are observing the triangle shape. This is the depression. Okay. Second layer we have to put or insert or apply or lie exactly depressions created by first layer. This is the first layer, two-dimensional hexagonal close packing first layer. Same layer, but the spheres are come, the triangle shape void is formed. Means void means the empty space which is not occupied by particles or constituent particles or atoms or ions. Okay, that is space is called what? Void. That space is what called what? Void. Okay, here the second layer sphere falls exactly on the depressions created by the first layer. This is the first layer. This is what? Second layer. Same. 1 minute. Depressions created by first layer. Okay, like this. Okay, when we apply second layer on the first layer, having a one tetrahedral void. See how it looks like this. These are the three spheres. One triangle shape void is formed. This is closed by, or this is filled by, this depression is filled by what? Second layer sphere. This is looks like, these are the triangle shape, trigonal shape. like this. These three are like this, and another one is above like this. This is the tetrahedral structure, isn't it? This is the tetrahedral void. This void is called what? Tetrahedral void, isn't it? The same layer, diffractions created by the this void is empty. This void is empty. Here also what? Sorry. This void is empty. Here this void is empty. This void is called what? Octahedral. The void which is surrounded by 4 spheres, it is called tetrahedral void. The void which is surrounded by how many spheres? Backside 1, 2, 3. Backside, first layer 1, 2, 3. Second layer 1, 2, 3. Isn't it? The void which is surrounded by 6 spheres is called octahedral void. Similar manner, where this side. This side sphere like this. This is the empty space. It looks like this is the tetrahedral void. The octahedral void looks like okay. Six spheres. This is the octahedral void. This void remains not closed. This void remains not closed. This is having a coordination number. Coordination number is 4. Tetrahedral void having coordination number 4. Octahedral void for having a coordination number 6. Remember the things. Tetrahedral void, it is having a coordination number 4. Octahedral void, it is having a coordination number 6. Got it? Okay. Then this looks like this. Like this it looks. Got it? This looks like a tetrahedral, or it looks like this. This 3, 1 is here. It looks like this, tetrahedral void, and octahedral looks like that. Okay. In the same manner, the conversion of hexagonal close packing in 3 dimension, we are adding another layer on this. We are adding another layer in this. How it looks? Placing third layer or second layer. Okay. In this arrangement, the covering tetrahedral void by first or third layer. Okay. In this arrangement, whatever the tetrahedral void is formed, this is the first layer, this is the second layer. This second layer makes the tetrahedral void. This tetrahedral void is covered by the third layer, that is A. The first layer we call A, second layer we call B, third layer we call A. Means it is having a similar arrangement. The spheres of the first layers falls exactly above the third layer, or third layer spheres of the third layer falls exactly above the first layer, not the second layer, isn't it? Means the spheres of the fourth layer falls exactly on the second layer, falls above exactly on the second layer, isn't it? Like this. This type of arrangement is called what? AB type. What it is? AB type. AB type arrangement means first and third layer are similar or same, and third and fourth layer are same, isn't it? Like this arrangement is AB type. By looking this arrangement, it looks like a hexagonal close packing. By looking what it is, a hexagonal close packing, isn't it? By looking, we are having a hexagonal close packing. This type of arrangement is appear in zinc and magnesium. This type of arrangement is appear in zinc and magnesium. Okay. Next, covering a tetrahedral void. This is the concept. Next, covering the octahedral void. Covering what? Octahedral void. Covering octahedral void. Covering octahedral void. Octahedral void. Covering octahedral void means the void which is surrounded by 6 sphere is called octahedral. The void which is surrounded by 4 spheres is called tetrahedral, isn't it? Okay. In this arrangement, the A spheres, the layers of the A is different, arrangement of the layers A is different, arrangement of the layers B is different, arrangement of the layers C is different. That's why this type of arrangement is called what? ABC type. ABC type. This type of arrangement is called what? ABC type arrangement. See here, the first layer is different, second layer is different, third layer is different. Then fourth layer, it is similar to the first layer. The third layer spheres or fourth layer spheres falls exactly above to the first layer, isn't it? Okay. The fifth layer is exactly above the second layer. Sixth layer is exactly above the third layer, isn't it? That's why this type of arrangement is called what? ABC type. Then it looks like a face-centered cubic close packing. Face-centered cubic close packing. FCC type of arrangement is observed. It looks like a FCC type of arrangement, octahedral void. FCC type of arrangement is observed. Here, NaCl, in NaCl, 2 tetrahedral voids are observed, 1 octahedral void is observed. The arrangement is n number of spheres are there. See, n number of spheres are there. In that, 2 tetrahedral voids are there and 1 octahedral voids are there. Remember the thing. Okay. Next, this type of arrangement is observed in aluminum, silver, aluminum, copper, etc. etc. This type of arrangement is observed. Okay. Okay. Next concept is defects in solids. Okay. All solids, all crystalline solids are not orderly arranged or perfectly arranged, having some defects or having some impurities or imperfection in that. Okay. Let us go one by one. What are the defects in the solids? Okay. Defects in solids. Solids means in a crystalline solids we are observing some defects, means they do not follow order at a particular points. That's why defects are classified into 2, that is line defect and point defect. Defects are classified into 2, that is point defect, line defect or point defect or atomic defect, line defect or electronic defect, line defect or electronic defect, line defect or electronic defect, isn't it? Okay. We take an example of ideal crystal. In ideal crystal, what happens? In ideal crystal, In ideal crystal, what happens in ideal crystal? The crystals which having a same unit cells and having a same lattice points throughout the crystal. Take an example of like this. This is the crystal. This is the crystal. This is the crystal. Having the same unit cells and same lattice points throughout the crystal is called what? Ideal crystal. But this ideal crystal is exist exactly 0 degree Celsius or 0 Kelvin. At a very low temperature, the solid exists as a solid behave as what? Crystalline solid is behave as a ideal crystal. Otherwise, they have some defects. At above 0 degree Celsius, they have some what? Irregularity, dislocations, impurities, or they do not arranged properly. Okay, ideal crystals is up. Having ideal crystals. Okay, we are having a point defects. In point defects, again we have classified into 3, that is stoichiometric defect, non-stoichiometric defect, and impurity defect. What do you mean by this stoichiometric defect? Stoichiometry means stoichiometric defect. Stoichiometric defect, non-stoichiometric defect, non-stoichiometric defect, stoichiometric defect, and impurity defect, Here, take an example of stoichiometry. Cations and anions are in the ratio. Means 1 calcium means 2 chlorine. They are all in the ratio. NaCl. Take an example of Na, 1 Na, 1 Cl. It is in the stoichiometry. Means it is in the perfect what? Ideal crystal. Having some defects means exactly both are missing or one is missing, like this. Okay, stoichiometric defects. In stoichiometric defects, again we are classified into stoichiometric defect. Again we are classified into vacancy defect, Stoichiometric means, got it? NaCl. This is the stoichiometry. 1 Na, 1 Cl. Means 1 Na, 2 Cl is not a stoichiometry. It's different. Its stoichiometry is different, isn't it? 1 Na means 1 sodium containing 1 Cl, or 1 sodium have 1 Cl. 1 calcium have 2 chlorines. This is the stoichiometry, isn't it? Similarly here also, what happens in stoichiometry? So many defects are observed. That is a vacancy defect, interstitial defect, Schottky defects, and Tranquil defect. What? Tranquil defect and Tranquil defect. Like this, in the stoichiometric defects, again we have 4 classification, and non-stoichiometric defects having again metal excess defect, and metal deficiency defect. Metal excess defect and metal deficiency defect. Impurities. It is not in your syllabus. Okay, got it? In stoichiometric defect, what do you mean by this stoichiometry? See here, Na, Cl, Na, Cl, Na, Cl, like this. 1, 2, 3, 4. Okay, like this. Again, Cl minus Na plus, Cl minus Na plus. Sorry. No, Na plus, Cl minus Na plus, Cl minus Na plus. Again, Na plus, Cl minus, Na plus, Cl minus, like this. See, this is a perfect stoichiometry. Means how many sodium atoms are there? 1, 2, 3, 4, 5, 6. Same, how many chlorine atoms are there? 1, 2, 3, 4, 5, 6. 6 ratio 6. This is the stoichiometry. Means 1 sodium have to 1 chlorine, isn't it? This is the stoichiometry. If having some chlorine is less, means it is not a stoichiometric defect. It is not a stoichiometry. It is not a perfect ratio. 6 sodium atoms are there, 5 chlorine atoms are there. It's not a perfect stoichiometry. Got it? Okay. Stoichiometry means number of cations and anions are in the equal ratio. That is called what? Stoichiometric defect. Okay, let us go in detail. That is in the stoichiometric defect. That is first in stoichiometric defect. First is vacancy defect. Vacancy defect. What do you mean by this vacancy defect? This vacancy defect is known that here some ordered arrangement, that is in the what? Stoichiometric ratio, that cations and anions are there. It is observed. This vacancy defect and interstitial defect are observed in non-ionic compound. Remember, non-ionic compound. Non-ionic compounds or substance. This vacancy defect is observed in non-ionic compound. Okay. Here some lattice points are vacant. Take like this. I am removing this constituent particle from this crystal. Some of the lattice points are missing or vacant. This type of vacancy, this type of defect is known as what? Vacancy defect. This is observed in the non-ionic compound. Remember. Okay. What happens here? In the crystalline substance, some of the constituent particles are missing from their lattice sites, are known as what? Vacancy defect. Similarly, interstitial defect. It is also observed in the non-ionic compound. Interstitial defect. The name itself indicates interstitial means some of the lattice points are occupied in the interstitial position. See, between these constituent particle, this is the lattice sites or interstitial. This is the lattice sites. This is the interstitial site. This interstitial site is occupied by another molecule or another atom or molecule, ion. This type of defect is known as what? Interstitial defect. See, the arrangement is there, ordered arrangement is there. Some of the constituent particles are occupy the interstitial positions in the crystal. Is this type of defect is known as what? Interstitial defect. Interstitial defect is known as what? Some of the constituent particles are occupy the interstitial sites in the lattice is known as what? Interstitial defect. Got it? These two are what? These two are observed in non-ionic compounds. Okay. Here density remains same. Here density remains same. In the vacancy defect, some of the lattice points are gone. That's why the density decreases. Okay. That's the density is what? Decreases. Okay. Next concept, that is Schottky defect. Next is what? This is the second, and next one is Schottky defect. Third one is what? Schottky defect. Schottky defect. In Schottky defect, here similar to the vacancy defect, but equal number of cation and anion are missing. In the Schottky defect, what happened? Equal number of cation and anion are missing. See here, this is the cation, this is the anion, cation, anion, like this. Here anion, cation is missing, again anion, cation. See here, cation, anion, cation, again anion is missing. Like this, here in the crystalline substance, missing of equal number of cations and anions in the crystal from the lattice sites is known as what? Schottky defect. What happens here? Here density is decreased. Here what? Density is decreased. Volume remains same, but density is what? Decreases. Got it? Next concept, that is these are having in Tranquil defect, some of the atoms are dislocated and occupy the interstitial site between the lattice points in the crystal. Such type of defect is known as what? Tranquil defect. But in case of Tranquil defect, cation having a very small size than the anions. Cations having a very small size than the anions. Here coordination number is very high in case of very low in case of Tranquil defect. In case of Schottky defect, coordination number is very high because the cation is very small. The cation is very small. Anions are very large. Anions are what? Very large. At that time, the coordination number is very low. In the same manner, in case of Schottky defect, what happens? The arrangement is having a similar atoms means they are having the high number of coordination, high number of atoms. They are having a high number of coordination number, isn't it? Okay. Here, in Tranquil defect, the cations are very smaller than the anions.